Good morning and a warm welcome, ladies and gentlemen, to another exciting edition of our Web Seminar Wednesday format. Today we have I think, really exciting presentation about a new resin system. I really look forward to this presentations. The two speakers are Daniel Bien from Materia and Jasper Steffens from the Fraunhofer ICT. And I don't want to spoil too much and don't want to say too much. I will directly hand over to these two gentlemen, and I look forward to the presentation. And I'll be back later for the Q&A session. Enjoy, everybody, and Daniel, Jasper, have a great talk.
Okay.
Thank you.
Thanks, Bastian. Thanks for the opportunity to present on this Wednesday. As Bastian said, we'll talk about a new resin system, DCPD resins. It's a thermoset resin with very low viscosity, and I also will cover later about carbon footprint and the options to recycle. A little bit of history. So you might wonder, I was introduced as a speaker from Materia. So that's the company ExxonMobil acquired. So Materia was founded in 1998 by Professor Grubbs, who was a professor at Caltech. And he invented a ruthenium-based metathesis catalyst. So I'm a chemist by education, so I knew the catalyst. And this company, the purpose of the companies was to commercialize it and to find applications. And the first one was in pharmaceutical products like macrocycles. So that would be something as a chemist you would think this can be used for. But there's a second application to make a polymer of DCPD using this metathesis catalyst, which is not obvious, but it's a great technology. And in between 2017 2021, the catalyst business has been spun off to Umicore. So they're actually sitting in Germany, former Degussa and Hanau. And an ExxonMobil partnered then with Materia to develop more this poly-DCPD market. And in 2022, so it's not that long ago, ExxonMobil acquired Materia, and that made a lot of sense for us as an oil company. So we have to look at different applications, what we can do with this with oil and gas besides burning it. And I mean, making composites obviously is a great opportunity and a sustainable opportunity. And as I indicated, we make DCPD ourselves, and we have options to make it in large scale. I have invited Jasper to join me because since 2024, Fraunhofer ICT in Winstal and we, Materia, have signed a collaboration agreement, and basically there are three purposes. One is to optimize high-pressure RTM process for these proximal resins, DCPD resins, to develop modeling capabilities for FEA and mold flow analysis. Jasper will talk about. And the last point I kind of forgot to mention, which is very, very important for you, it's also like our technology center, and we invite you to come and you can work projects together with us. And Jasper will talk about that a little bit more. So for those of you who like to see a little bit of chemistry, so this is a DCPD molecule. So DCPDs are two cyclopentadiene molecules which react with the Diels-Alder and make this nice molecules. We also sometimes add norbornene, and then we add the catalyst. So it's a two-component system, but not like you have that in PU or in epoxy. It's the monomer, the liquid monomer formulation, and then we add a catalyst which is only 2%, right? So, and then you perform this metathesis, and then you make structures like this, which is what we would call a thermoset polyolefin. So what is so exciting about it? I think most importantly is a very, very low viscosity. So it's below 20 centipoise at room temperature. So you can imagine what that means, and I'll talk later a little bit more about it. Has excellent stiffness, toughness balance, is a little bit lighter weight, so 10% lower density. And then because of the chemistry, it's only hydrocarbon, it's very hydrophobic, so and has a very, very good chemical resistance towards, especially towards acids and alkali. But also towards other hydrocarbons. I must say, we have done some good tests. The reaction being a metathesis, so ring double bond opening and recombination, it has a relatively low exotherm, which I show you later as well. Has good operating temperature range, and that's basically the trick with the system. By using different catalysts, you can control the pot life, you can control the curing temperature, and so on. And that gives you a lot of flexibility. It's once it starts curing, it cures very fast. I show that later to you as well, and has a very low carbon footprint. Show you later some data, and also there are options to recycle. Here a little bit like an illustration what the DCPD polyolefin thermoset could mean. So when you think of polyolefins, you probably think more of those long hydrocarbon chains, which give good impact toughness, but have obviously poor thermal properties. On the other hand, I mean, you have a very highly cross-linked chains in a thermoset, and then usually you have heteroatoms, which gives you poor chemical resistance, and then I mean the DCPD polyolefin thermoset gives you a good combination and has that good impact toughness, but also very, very good chemical resistance. So I promised to give you a few examples. This one is a quite complex tool, complex part we made with high pressure RTM processes. So you see there's a foam insert, and so it's quite complex geometry. So the fill time, because of the very low viscosity, were only 10 seconds, and cure time less than 50 seconds. So you can imagine the potential in like RTM processes. We can use DCPD resins, for example, in leaf springs, as shown on the left side. And if anybody among you works on leaf springs, I mean, Jasper and I, we have a very nice project going where we can do simulations and material testing. So that's an exciting, very exciting project. So we can obviously use different technologies. So here an example of hydrogen tanks using filament winding. And so we have done already a number of examples. I'm very proud. I've recently worked with the University of Wrocław. And without any help, I mean, they were able to produce a quite good hydrogen tank. Typically, we would see improved burst pressure and also improved burst pressure after the drop test. We work on, or we can do type 4 tanks, but we also think about type 5 tanks where the liner could be DCPD. So that's an interesting field where we actively work. RIM is a little bit more traditional for DCPD resins. But there we have a long experience. This is an top of an acid tank done by RIM. And so that has lasted already almost 10 years. So very good example here. probably none of you will make wind turbines, but just as an example, this is a rotor blade of a wind turbine. Vacuum is applied, and application was like 5 times faster than fusion speed. So as you would expect, due to the low viscosity, we do pultrusion. These are rebars, and again, I mean, we have some experience there, and I know I work with some of the CU members in that field as well. Just to show off a little bit, this is a nice part we made for Corvette owners. So you can basically replace parts with carbon fiber parts. So this is all been done with Vacuum by McLaren in the US, and this is the C-Class A with carbon fiber. This is a piece we just came from Jack, which we had displayed. So this is a model of a battery box. We'll improve that, but just to show you, I mean, this has a dimension of 130 by 80 centimeters, and injection time was only 15 seconds. So to summarize, again, very low viscosity, 20 times less, very low density, is further lightweighting. It is tougher, 5 times tougher, and has a very fast cure. Here, a few examples of the toughness. So here, an example where we had a falling object test or falling weight test, the impact of Proxima compared to epoxy. So you see the impact is much smaller. Also, like, so I can, the crack resistance of Proxima versus epoxy, so you can see you get much higher loads and lower displacement. We have also the data behind this, and being a Texan company, we have shot on our Proxima resin, and so it absorbs the impact. And later I can show you a little bit in the video as well. But that's actually on the Jack, I mean, that also caught the attention, and we have some more interest in defense, which for sad reasons maybe we will need more in these times. All right.
Right.
Yeah.
Should I take over for the collaboration now?
Yes,
Thanks.
please.
So, hello everyone. Nice to be here. Have a chance to present to you guys. What I would like to go into a little bit is the collaboration hub that Daniel already mentioned. So at Fraunhofer ICT and Finstal, we have established the European hub for all research activities regarding RTM with the Proxima resin system, that's the DCPD solution by ExxonMobil. We are currently procuring the HPRTM equipment, so this is very fresh, early days. However, as Daniel mentioned, we already have projects ongoing with different interested parties. And these trials obviously needed a way to make parts, so we have started in wet compression molding. You can see on the right there, there's basically a picture from our lab showing maybe quite visually how low viscous the material is. In this case, it's being applied to carbon fiber fabric. And here permeation is, even though it's a dense carbon fiber, it's very easy. You may have seen that as well on JEC. So we showed a couple of plates there. For example, for carbon fiber, we were able to achieve 65% volume fraction in wet compression molding. That's quite high. And we can basically build on that once the HPRTM equipment is available. What we're going to be doing in the collaboration hub is focus on the processing parameters, do detailed analysis of the mechanical properties of the resulting composites, and then do in general a feeder activity to the activities at Exxon regarding the overall LCA and end-of-life solutions for Proxima, as the RTM application is only one of the various applications for this type of polymer, for the system that Exxon is selling here. So we are feeding into that, and for the process itself, for the RTM process, we will do an in-depth LCA, so we'll be gate to gate, able to give you information to evaluate the process and compare it to others. On the next slide, we have an overview a little bit on what we're planning essentially for this year and the next. As I mentioned earlier, we will have an HPRTM unit, so that will come this summer. We'll then commission it at Fraunhofer ICT, and that is open for customer trials. I mentioned we will do our own trials. We will focus on the process guide that is supposed to result from this, so give you, in the end, a good handbook to understand all the relevant process parameters to set the process up yourselves. This is what Exxon is funding essentially for a better industry adoption to take out a lot of the uncertainty early. However, if there's dedicated or a specific interest already at this stage, then we are more than happy to work on specific projects already. ICT might be known in this space, so we have quite large presses and we have some base tooling available to make rather economical first geometry or trials of first geometries, but we can always also run customer-specific toolings, and then obviously contribute our analytical capabilities to understand the behavior in those parts. Finally, at Fraunhofer ICT, we are providing data inputs to activities running at Simutens. Simutens is a spin-off from KIT. They are also quite well known, I think, in this space again, and they will be working with our data to provide a virtual set of virtual methods to describe all relevant aspects of RTM with Proxima. We've brought a couple of examples on the next slide here. So what we've currently achieved already, we fed the data, generated data and fed it to Simutens for them to build a curing kinetics model, and also to understand the reactive viscosity. So this is a quite complex field to model, but we have seen first good results. Obviously, these models will be finalized over the duration of the project, but already now we've seen the first form-filling simulations for improved designs of the part Daniel showed earlier, in addition to understanding the structural performance. Also here we have first data that we've used to do static and some dynamic impact simulations for a part for the automotive application that will serve as one of the demonstrators in this project. And all of these solutions, so the curing, the reactive viscosity, and essentially running a curing curve, understanding how the behavior would be at different processing temperatures, that can all be accessed online. So if there's interest here to understand specific process profiles, maybe replicate what you have in terms of set points, see how Proxima would behave in that regard, do reach out to us. There are licenses available through Exxon for the Simutens hub that can be found online. You may also direct a request to Simutens directly. They will reach out. So we are working in tandem here on these activities. So to sum up, quite a lot of hardware coming, enabling us to do a lot of projects. And we're very open to include any other interests here for this resin system. And then also, if it's easier to do that virtually, we are more and more able to already answer questions of processability and process advantages for your products on a virtual level before doing any kind of trials.
Yeah, thanks, Jasper. So, yeah, I just want to repeat what he said. We invite you also to use Fraunhofer's facilities, and I mean, I enjoy really working with them. They're very experienced. They motivated and provide a super service, and so that makes it easier to test our material. Yeah, I wanted to. Oops. Let's see. So, I wanted to conclude the presentation with a video. There's a little bit of repetition in it, and then it ends with the questions of carbon footprint and recyclability. So there's no music, so I can talk about it. Yeah, so this is a first example. Now you see how Proxima looks. Is a little bit viscosity, almost like water. We add the catalyst to it, and then you can see it can cure instantly. And what you also see is that the exotherm is not that strong, right? So I think with other systems, I mean, would have a much stronger exotherm. Here's a repeat. So gel time only 3 seconds, and then polymerization takes 6. I mean, that is just an illustration. So we typically would not use a system like this, but you can kind of see what the potential is. So we can use different catalysts. So curing at let's say higher temperatures. So in RTM, we talk usually like 90, 100 degrees C. So this demonstrates again the low viscosity and what it does, like in the Vatem process. So it also would illustrate the fast mold filling here on the left side, the 3100 with the C32 catalyst. So it really races, and then on the right side you have a comparable epoxy grade. And yeah, that's mainly due to viscosity. So there's not a real surprise here. So in that case, it was like 20 times faster. You remember I showed you the example of the wind turbine, which was like 5 times faster in real life. Yeah, so this is basically what we say. It's in the upper right corner, high toughness and high infusion speed. So as promised, here a video of the test we did on the toughness. So with the bullet, and again, so it fully absorbs the bullet. Now we talk a little bit about the lower carbon footprint. So what we've done here, so this is the CO2 emission cradle to gate, and it's a carbon foot per liter carbon footprint estimate. So Proxima is being 2.8 and compared to an epoxy 7.3. Why is that? Because Proxima is generated, or the DCPD is generated during naphtha cracking, and that is a one-step process. So compared to the other processes, relatively low carbon intensive. Obviously, you can use also natural feedstock, hydrocarbon natural feedstock. Then you go lower here, but this is based on crude. So move on. So, and let me just see what's next. So now we come to recyclability. So here you see an example of our unit in Baytown in Texas, where let me just stop here, where we feed plastic waste into our unit. So ExxonMobil is a large polymer producer, probably the largest in the world in terms of polyethylene, I believe. So we have also responsibility to take back plastic waste, which you cannot mechanically recycle. And so we have developed the advanced recycling method. So we have JVs to collect plastic waste and take it back into the unit. So here these are granules. They're fed into a hopper, and then it's suspended in an oil and fed into the unit. And that's something we have proven works as well with Proxima. So we have run that through the process. So, and there's no surprise because Proxima is a pure hydrocarbon, so can be recycled and basically brought back into the system. So in principle, I don't know, at one point we may be able to certify versus mass balancing. Potentially circularity because it could end up in naphtha cracking as well, but that's not proven yet. But I can see that being possible. Then is the question, obviously, how you separate the fiber from the resin, and we've done also some research on that. So, I mean, textbook is pyrolysis or solvolysis or other methods, and we have tested them all, and we have some very promising leads, which at the moment I cannot disclose. But I mean, I've seen the data, and I'm very, very positive that also that step can be done very efficiently with Proxima. Yeah, so Exxon will do 1 billion pounds, so 500 ktons a year of recycling in 2027. So that's basically the summary. We have lower carbon footprint, low viscosity, reduced cycle times, lower weight reduction, and very damage resistant, excellent fatigue properties. And so, yeah, I hope that entices you to test the material, and yeah, we can do that at your site or as offered at Fraunhofer site. And I'm very keen to hear your questions and to work with you.
Yes, Jasper, Daniel, thank you very much for this very interesting presentation.